In this presentation, we will discuss some of the regulations governing brominated compounds. This work was prepared in collaboration with Butts County by researchers at the University of Georgia, with financial support from Butts County and a regional water plan seed grant from the Georgia EPD. As of 2019, only 11 of the approximately 700 disinfection byproducts, or DPB, species that have been identified are regulated by the U.S. Environmental Protection Agency. 4 of these DPBs belong to the trihalomethane group. 5 are haloacetic acids, and the final 2 are bromate and chlorate. The first regulation of DPBs in the U.S. was established by the U.S. EPA's Total Trihalomethane Rule in 1979, which set a maximum contaminant level for trihalomethanes present in finished drinking water. This regulation was created to strike a balance between the risks of reduced efficiency in removing waterborne pathogens and the creation of potentially carcinogenic DPBs, while keeping technological and economic constraints of water treatment plants in mind. Since the specific health risks associated with each species of DPB were relatively unknown, the regulation was based on the sum total of trihalomethanes present in finished drinking water. However, the subsequent identification of several additional classes of DPB in drinking water and a growing understanding of the potential toxicological and carcinogenic effects of individual species of DPBs lead to the creation of new maximum contamination level and maximum contaminant level goals in the United States. Current laws regulating drinking water disinfectant and disinfection byproduct regulation include the Stage 1 and Stage 2 disinfectants and disinfection byproduct rules, or the DBPR. These regulations apply to community water systems and to non-transient, non-community systems that apply chemical disinfectants to drinking water at any point during the treatment, and this is regardless of the number of customers served. The Stage 1 DBPR went into effect from 2002 to 2004 and expanded regulations to include other species. Under the Stage 1 DBPR, the maximum contaminant level for total trihalomethanes was lowered, and the maximum contaminant level goals were created for individual DPB species within the regulated groups. It's important to note that the maximum contaminant level goals are non-enforceable public health objectives that do not consider technological and economic constraints of water treatment plants when defined. However, the maximum contaminant level is a legal threshold, and it is an enforceable regulation that does consider practical constraints on water treatment facilities. The Stage 1 DBPR also created maximum residual disinfectant levels for chlorine, chloranamines, and chlorine dioxide. Finally, the Stage 1 DBPR created a schedule and protocol for collecting DBP monitoring data at various stages of the treatment process. The Stage 2 DBPR went into effect between 2012 and 2013 and supplemented the regulations established by the Stage 1 DBPR. Under Stage 2, water systems are required to identify areas of high DBP production within their treatment process for use as sampling sites. Each of these monitoring sites must have DBP levels in compliance with the maximum contaminant levels for total trihalomethanes, HAA5, bromate, and chlorite, and this is referred to as the locational running annual average. This average measure addresses a gap in the Stage 1 DBPR compliance regulations, which allowed parts of a water distribution network to exceed DBP maximum contaminant levels as long as the network as a whole averaged DBP levels below the maximum contaminant level. Overall, international regulations for DBPs are very similar to maximum contaminant levels under the Stage 1 and Stage 2 DBPR in the U.S. For example, in the U.S., the maximum contaminant level for total THMS is 0.08 milligrams per liter, and guidelines for Europe, Canada, China, and Japan have been analogously set at 0.1 milligrams per liter for total trihalomethanes. U.S. regulations for bromate and chloride also compare to China regulations in China and Canada, but there is greater variation in the regulation of haloacetic acids, with only the U.S. and Canada regulating the sum of the 5 species, Japan and Australia regulating the individual concentrations of the 3 species, and China regulating individual concentrations of 2 species. The guideline concentrations for regulated haloacetic acids also vary widely, with the HAA5 limit set at 60 milligrams per liter in the US and 80 milligrams per liter in Canada, and individual species limits from 0.02 to 2 milligrams for China, Japan, and Australia. Europe does not currently regulate any haloacetic acids, but there is a proposal for the revision of the EU Drinking Water Directive to include limits on HAA levels. Among the data available for global DBP regulations, Australia is an outlier in that its regulations allow much higher levels of trihalomethanes, 3 haloacetic acid species, bromate, and chlorite. Finally, the World Health Organization has set regulations on individual trihalomethanes, regulations concerning the maximum contaminant levels for DPBs and the protocol for monitoring the concentration of these DPBs throughout the water treatment process have been established to limit human health risks associated with using chemically disinfected water for drinking, food preparation, and bathing. The regulations attempt to strike a balance between disinfection of waterborne pathogens and minimization of DBP creation, while keeping the technological and economic constraints of communities in mind. Thresholds for DBP levels in finished drinking water were chosen to reduce public health risks based on available toxicological and epidemiological data. The classes and individual species of DBPs were selected because trihalomethanes and haloacetic acids make up the majority of DPBs in finished drinking water following disinfection by chlorination. Further, the trihalomethanes and HAAs were thought to be surrogates for the hundreds of unregulated and unmeasured DPB species potentially present in finished drinking water and indicators of the toxicity and human health risks associated with water use. Unfortunately, there is strong scientific evidence that the current Stage 1 and Stage 2 DBPRs fail to protect water consumers from exposure to potentially harmful species and concentrations of DBPs. U.S. regulations of DBPs have been updated several times since the first discovery of DBPs in finished drinking water in 1974. However, as argued by Singer in 2006, these changes have consistently failed to consider scientific evidence showing that the 11 regulated DBPs are inadequate surrogates for the complex mixtures, potentially hundreds of DBPs present in drinking water. Therefore, they may be poor indicators of the health risks associated with water use. Only 5 of the 9 bromine and chlorine containing haloacetic acids are regulated. The decision to only regulate 5 of these HAAs was made when analytical constraints limit the ability to quantify 4 of the unregulated HAA species. By the mid-1990s, the importance of the 4 unregulated species, which account for between about 20 to 50% of HAAs, especially for water sources with elevated bromide levels, was recognized. Despite the commercial availability of standards for the 4 unregulated HAAs before the finalization of Stage 1 DBPR, only 5 of the 9 were included for regulation. The Stage 2 DBPR also failed to define maximum contaminant limits for the 4 unregulated HAA species, meaning that our current regulations do not accurately safeguard public exposure to haloacetic acids. The regulation of HAA5 instead of all 9 species is particularly important when considering source water with elevated bromide concentrations. When source waters containing high levels of bromide are disinfected with chlorine, DBP formation shifts to a greater proportion of brominated species, including the 4 unregulated brominated haloacetic acids. This means that the HAA5 measure underestimates haloacetic acid exposure, especially if the source water contains high levels of bromide. Trihalomethane and haloacetic acid levels are regulated based on the sum total of species on a milligram per liter basis in a given water sample. What this means is that the weights of individual species are added up to quantify the total trihalomethane and haloacetic acid 5 levels. Since the molecular weights of disinfection byproducts increase with bromide the incorporation of bromide, species containing only chloride have a higher weighting factor. This is a problem because of some of the chlorinated regulated species, such as chloroform, are considered less dangerous than brominated compounds like bromoform, which can lead to the misrepresentation of public health risks of a given water sample. Regulating trihalomethanes and haloacetic acids as group sums is not appropriate because the human health risks associated with DBP exposure vary between species. This means, again, although two water samples may have the same total trihalomethane or haloacetic acid values, the risks associated with consuming those water samples can be dramatically different depending on the proportions of individual species that are contributing to those sums. This is especially true for source waters with high bromide concentrations, as there are greater health risks associated with brominated disinfection byproduct species. There's no evidence that the 11 regulated disinfection byproducts are surrogates for the unregulated disinfection byproducts. And what this means is that they may not successfully be used as indicators of public health risks associated with water consumption. There is evidence that the unregulated and often unmeasured disinfection byproducts are drivers of toxicity. And this is particularly concerning as water utilities are switching to alternative disinfectants, and this includes chloranamines, ozone, and chlorine dioxide, in an attempt to comply with Stage 1 and Stage 2 disinfection byproduct rules. There's much less data on disinfection byproduct formation and associated health risks of water consumption following treatment with alternative disinfectants. Recent work suggests that although alternative disinfectants may reduce the levels of regulated DBPs, these methods may promote the formation of unregulated byproducts that are potentially more problematic to human health. Increased formation of unregulated disinfection byproducts with alternative disinfectants is of particularly concern if source waters contain elevated levels of bromide. Because there have been no human or health risks associated with bromide in itself, discharges of bromide to surface waters has not been regulated in the United States. However, an accumulation of scientific evidence over the past 40 years has identified bromide as an important precursor of disinfection byproducts. Brominated DBPs, again, are more toxic than their chlorinated analogs, meaning that there's a potentially greater human health risk associated with consuming water containing brominated DBPs. Greater source water bromide levels can also increase the formation of unregulated classes of DBPs and potentially be more problematic than regulated species. The U.S. EPA has added bromide and total organic carbon, another important precursor to disinfection byproduct formation, to the Safe Drinking Water Act as of 2016. This means that the EPA has required drinking water utilities to monitor bromide and total organic carbon to establish occurrence data that can be used to consider future regulation. The U.S. EPA has also included several haloacetic acid groups containing brominated species in this new regulation. The most recent contaminant candidate list, which is a list of priority chemicals and microbial contaminants selected by the U.S. EPA for information collection and future regulation consideration, includes several nitrogen-containing disinfection byproducts and bromochloromethane, which is used as a fire extinguishing fluid. Additionally, there's currently a plan to investigate the impacts of oil and gas industry wastewater discharges on drinking water quality in the U.S. EPA's final 2016 Effluent Guidelines Program plan. The biennial Water Analysis, Emerging Contaminants and Current Issues review, published in the Journal of Analytical Chemistry, provides an excellent overview of updates on the U.S. EPA water contaminant monitoring and regulations, as well as a summary of the latest published research findings concerning emerging water contaminants and analytical methods.